Welcome back. So we're talking about second-order linear ordinary differential equations. We have shown how to solve these a number of ways, and now I'm just going to give you a bunch of examples, and we're going to work through them to build some real intuition for these problems. So the first one I'm going to do is x double dot plus 3x dot plus 2x equals 0. And if you like, you can kind of pretend that this came from a spring mass damper system with mass 1, spring constant 2, and damping coefficient 3, whatever you like, it doesn't really matter. Okay, this is a second order linear differential equation. And we're going to solve this a couple of ways, and then I'm also going to plot the solution in Matlab or Python. And so in addition to having this differential equation, we also need its initial conditions to uniquely specify the solution. And so we're going to say that we have x at time 0 equals 2, and x dot at time 0 equals, I think I want to say that this is minus 3. And I've solved this problem ahead of time. This is the kind of problem I would give on like a midterm or an exam or a homework, because all of the coefficients are integers and everything's going to work out nicely. It doesn't have to be that way, but that's kind of how I've chosen this. So these are my initial conditions here. Okay, and this is a pretty easy setup now. We know how to solve these systems. We know how to work with these. So I'm just going to do it. The basic idea here is that we are going to guess the solution. We're going to try x of t equals e to the lambda t. And we're going, because we know that e to the lambda t is kind of the base solution of all linear ordinary differential equations, or at least we're starting to suspect that that might be the case. And that is because when I take the derivative x dot of t, I get a constant lambda times my original function e to the lambda t. So my derivative is just a constant times x. My second derivative, x double dot of t, is just lambda squared e to the lambda t, which is just another constant times x of t times e to the lambda t. And so any amount of derivatives I take of this e to the lambda t, I'm going to get a constant times e to the lambda t, which means that if I plug all of these into my differential equation, I'm going to get kind of a polynomial in lambda times e to the lambda t. So let's do that right now. So we're going to plug this into our ODE. Maybe I'll switch colors, like green right now. And so I'm just going to literally plug x double dot in here, and x dot in here, and x in here, and we're going to equate all of the terms. So I'm going to get a lambda squared e to the lambda t, that's my x double dot, plus 3x dot is 3 lambda e to the lambda t, plus 2x, that's plus 2e to the lambda t, and all of that equals 0. All of that equals 0. And so, again, we've done this before. I'm going to do this a bunch of times, and in the next lecture, I'm going to show you what happens when you have higher order differential equations with more derivatives, x triple dots, x quadruple dots, and things like that, and nothing's going to change essentially. So every single term has an e to the lambda t, because all of my derivatives have an e to the lambda t. And so I can factor that out. And so I get just my stuff with lambdas, lambda squared, plus 3 lambda, plus 2 times e to the lambda t equals 0. Now, e to the lambda t essentially never equals 0, except when lambda t is negative infinity, so this is basically not going to happen. So the only way that this expression can equal 0 for all time is if this polynomial in lambda equals 0. And this is called the characteristic polynomial, the characteristic polynomial. And specifically, sometimes we call it char of lambda. Okay, that's fine, the characteristic polynomial. But essentially, it is that lambda squared plus 3 lambda plus 2 equals 0. Okay, those are the specific lambdas. So those are the specific lambdas so that for those lambdas that satisfy this characteristic polynomial, then e to the lambda t will satisfy this differential equation. Okay, so I plugged in this e to the lambda t and all of its derivatives into this differential equation, and I found this condition that has to be true for that lambda for this equality to hold with these coefficients. So the lambda that satisfies this is the lambda that will work in this solution. And now you're starting to see that I chose these coefficients to be as easy as possible. So you can just factor this polynomial. You say, well, maybe I'll switch colors again. Maybe I'm feeling orange right now. Okay, so I've got something like lambda plus 2 times lambda plus 1. That, if I multiply this out, I get lambda squared plus 2 lambda plus lambda is plus 3 lambda. So lambda squared plus 3 lambda plus 2. Okay, so that is my characteristic polynomial, equals 0. And this implies, of course, that lambda equals -2 and lambda equals -1 are solutions. Okay, those are two solutions to this characteristic polynomial. Lambda equals -1, we'll solve this, and lambda equals -2, we'll solve this. Let's just verify. -1 squared is 1, -3 is -2, plus 2 is 0. Good, this solves it. Let's try -2. -2 squared is 4, -6, so 4 minus 6 is -2, plus 2 is 0. So this also solves it. Both of these lambdas solve my characteristic equation. And so if I took e to the lambda t for either of these lambdas, it's going to satisfy this differential equation. Okay? In fact, that might not be a terrible thing to show. So I'll write down my solution. My solution is going to be x of t equals, and it's going to be some combination of these two e to the lambda t's. I have an e to the let's call this lambda 1 and lambda 2. This is going to be some constant c1 times e to the lambda 1 t plus another constant e to the lambda 2 t, and we're going to determine these constants from my initial conditions. So specifically, lambda 1 is -1. I'm just literally going to write this out. This is c1 e to the minus t plus c2 e to the minus 2t. And from my initial data, I know that x at time 0 equals 2. So if I plug in 0 for time, e to the 0 is 1, e to the 0 is 1. And so I get, x at time 0 equals c1 plus c2, and that has to equal the constant 2. Similarly, I can compute x dot. And x dot is going to be minus c1 e to the minus t minus 2c2 e to the minus 2t. And so x dot at 0 is minus c1 minus 2c2, and that has to equal -3. Okay, now again, I chose these coefficients to be like trivially easy. You can almost read off just from seeing it that if c1 equals 1 and c2 equals 1, 1 plus 1 equals 2. And -1 minus 2 is -3. So these coefficients you can just kind of read off. C1 equals C2 equals 1 would, in fact, satisfy both of these initial conditions. If you like, you can solve this a little bit more methodologically. You can write down the system, and you would say, okay, C1 plus C2 equals 2. That's this equation. And minus C1 minus 2C2 equals -3. And then I would go through my linear algebra of kind of solving for C1 or solving for C2. I think what I would do is I would add these together, and I would get something like, the C1s cancel, and I get minus C2 equals -1, which of course implies C2 equals +1. Equals +1, and then if C2 equals 1, then C1 has to equal 1, and we're done. 1 and done. Okay, so kind of easy to solve for these initial conditions, to solve for these coefficients with these initial data. We get that C1 equals C2 equals 1. And so literally I can just, I'm just going to erase this and write down the actual solution of my differential equation is x of t equals C1 was 1, so e to the minus t, C2 is also 1, plus e to the minus 2t. That's the solution of my differential equation. Okay, so really easy. We guessed exponentials, we computed their derivatives, plugged them in, and found this characteristic polynomial in lambda that had to equal 0. This had to be true for that lambda to be a solution of this differential equation. Okay, and then we found that lambda could be -1 or -2. I'm going to call these eigenvalues because in my mind they're eigenvalues of another system I'll show you in a minute. And then when you plug these in, Here, you can solve for the coefficients. Any linear combination of e to the minus t and e to the minus 2t will work. You know, lambda equals -1 or -2. Any combination of those will be a solution of this differential equation. But only a very specific constant 1 and constant 2 will satisfy this initial data, so we solve for that down here. And this is the specific solution that satisfies this differential equation with these initial conditions. Good. Okay, easy to do. So maybe one thing I will do is, you know, like, it's pretty easy to verify that this e to the minus t actually satisfies this. I'll just do that really, really quickly because I said I would. So, you know, if I took e to the minus t, that's e to the lambda 1t. Let's say that's one of my solutions. I'm just going to verify that if I take its derivative twice, so x dot equals minus e to the minus t, and x double dot equals minus is plus e to the minus t. And if I plug these into my differential equation here, I get, you know, e to the minus t plus 3 negatives minus 3 e to the minus t plus 2 positives plus 2 e to the minus t, yes, in fact, equals 0, because I have 1 minus 3 plus 2, that's 0, e to the minus t is equal 0. So I'm just confirming that, yes, this e to the lambda t does satisfy this equation, specifically because that lambda satisfied this characteristic polynomial. Good. Okay, I'm actually ready to plot this. So what I'm going to do is I'm going to erase this stuff. When we might derive one more equation, and then I'm going to plot the solution of this differential equation. So stay put. Okay, so I just erased some stuff and moved some stuff around so I have some place to work. This was the solution of this differential equation for these initial conditions. We had these two lambdas. We guessed a solution e to the lambda t, and these were the two lambdas that worked, lambda minus 1 and lambda minus 2, which were satisfy our characteristic polynomial in lambda. Okay, and again, I'm going to show you that we can also write this as a matrix system of differential equations, because in Matlab or Python, we might solve it using that matrix system, and I'm going to look at the eigenvalues of that. So just very quickly, maybe I'll do this in green again. I have that for this equation, I can always write, instead of just in terms of second derivatives of x, I can introduce a new variable, x and v, and ddt of that state is now going to be a system of first order differential equations in x and v. This is only first order because I only have a single derivative. And specifically, we're going to say that x dot equals v. So, so this is 0, 1 on the first row. X dot equals v. And the second row is going to be v dot. V dot is x double dot. If x dot equals v, then v dot is x double dot. And it's all of this stuff if I moved over to the right. So minus 2x minus 3x dot. So minus 2x minus 3x dot, which is v. Okay? And so this system of equations is equivalent to this, this single second order ODE in a single variable is equivalent to this system of two first order ODEs in x and v. And you can always do this. You can always go kind of back and forth. If I had a fifth derivative, I could write this as a system of 5 coupled first order equations by adding a state for every derivative. I've added a state v. Oh, my video is done processing. That's great. I've added a state v for x dot, and so on and so forth. Okay, and this is going to be my A matrix, and specifically the eigenvalues of this A matrix are in fact the solutions of my characteristic polynomials. Okay, so I'll, in fact, I should just show you that right now. Maybe I'll just do that before I go to Matlab and Python. What I'm going to show you is, in fact, the eigenvalues of this A matrix are the solutions of my characteristic polynomial. So I'm going to have a whole set of lectures on eigenvalues and eigenvectors, so don't freak out if you don't remember what I'm about to write down. But if I want to compute the eigenvalues of A, I literally take the determinant of A minus lambda times the identity matrix, and I set that equal to 0. And so A minus the identity matrix times lambda is A minus 2 minus 3 minus lambda times the identity matrix is just a diagonal matrix with lambdas. This equals minus lambda 1 minus 2 minus 3 minus lambda. And now I take the determinant of this, and the determinant of a 2 by 2 is pretty simple. It's the product of the diagonals minus the product of the off diagonals. And so the determinant of a minus lambda I is this thing, which is lambda squared plus 3 lambda minus 2, because you subtract the product of the off diagonal, so minus the product is 2, so plus 2, and that whole thing has to equal 0. And hey, would you look at that? This equation for the eigenvalues lambda, lambdas are now the eigenvalues of this A matrix, this is exactly my characteristic polynomial. So the eigenvalues of A will satisfy my characteristic polynomial, and the solutions of my characteristic polynomial are eigenvalues of A. Very, very useful, very, very important property. Okay, I'm going to, again, have a whole lecture showing all about this, probably multiple lectures. I just wanted to show you this here, and now I'll get back to plotting real quick. Okay, so yeah, this was just showing the eigs of A, the eigenvalues of A are in fact solutions of my characteristic polynomial, so they're going to be lambda equals minus 1 and lambda equals minus 2. Those are going to be eigenvalues of this A matrix. Okay, so deep, deep connections between eigenvalues and the solutions of my linear ordinary differential equations. In fact, that's how I think of eigenvalues. If you corner me and ask me what's an eigenvalue, I'm going to say, well, when you have a system of linear differential equations, the eigenvalues are, tell you what the solutions of that system are going to be. Good. So I think what I want to do now is just code up this example and show you, kind of plot some stuff and convince you that these eigs are the same. So first thing I'm going to do, clear all, close all, CLC. And maybe what I'm going to do here is just create my A matrix. So A equals 0, 1, semicolon, minus 2, minus 3. Okay, that's my A matrix. Let's see if it runs. Okay, this is A. That's my A matrix. And now if I look at the eigs of A, these had better be minus 2 and minus 1. Excellent. Okay, so we have confirmed that the eigenvalues of this A matrix are in fact the solutions of my characteristic polynomial, which are going to be the lambdas that work for the solution of this differential equation. Good, so that's a huge check right there. In fact, that's probably the biggest thing I wanted to show you, is that that's true. And now what I'm going to do is I'm going to actually plot this analytic solution. We solved this by hand, so it's analytic. That's what that means. And then I'm going to numerically integrate this differential equation using the built-in kind of, small time step integrator in Matlab, and I'm going to show you that those plots almost perfectly match each other. Okay. So I'm going to create a time vector from 0 in increments of 0.01 to 10. So this just means that this is a vector of time from 0 to time 10 with time steps of 0.01. And I'm going to start with an initial condition of 2 semicolon minus 3. That's what I had here. X naught is 2, V naught is minus 3. So I'm just creating this big initial condition vector of X naught and V naught, 2 and minus 3. And I think first I'm just going to plot x equals the exponential of minus t plus the exponential of minus 2t. That is like my analytic solution here. And we're going to plot t versus x. Maybe I'll make it a little bigger because this is a small font, line width 2 to make it a little bigger. And I'll just plot that for now. Okay, something doesn't like. E to the minus 2 plot. I probably just typed something badly. Let's see. Oh, you can't do 2t, it's 2 times t, of course. Okay, good. And maybe I'll make my font set GCA font size 24. Okay, and so this is my plot. I should probably put axes on. I would get upset if my students didn't. So this would be time on the x-axis, and this is the position x on the y-axis. Good. So that's that's my x label time, and maybe I'll just do that. So I think this is good for you to see. X label would be time, and y label would be my solution x. Okay. Good. Okay, good. So time and my solution x. And as you expect, this thing exponentially decays. This is what we solve for, this is what we find here, and this is the solution plot. So now what I'm going to show you is we can also numerically integrate this ODE. Why would we want to do that? Well, we can solve this by hand, no problem, it was easy. But if I added some nonlinearity or I made this a little nastier, we wouldn't be able to solve it by hand anymore. And so we'd have to integrate it numerically by taking little time steps and approximating how x evolves in time. And so it's nice to just be able to do that pretty easily. And so I'm of course going to write this as a big matrix system of equations. I'm going to say that this is, this whole state here, this vector of x and v, is this bold y. And I'm going to say that bold y, if I take ddt of bold y, that equals a times bold y. Okay, that's fine. This is a vector y, this is a vector y, this is a matrix. This works. This is a matrix system of differential equations. And so there's a built-in integrator called ODE45, which basically will integrate. I'll just write down the syntax and then explain it to you. ODE45 is a built-in, very accurate integrator built on a Runge-Kutta, a fourth-order Runge-Kutta time stepper with an adaptive time step. So it'll make its delta t smaller or bigger depending on how accurate the solution is. I'm going to have a whole lecture on this, so don't worry about it. ODE45. And ODE45 expects these three arguments. This is very similar in Python that I'll show you in a minute. So it expects the right-hand side, so ddt of y equals what? What's on the right-hand side? ODE function is the stuff on the right-hand side. It expects a time span, that's 0.01 to 10, and it expects an initial condition y naught. So to create this function that it's expecting, this right-hand side, I'm literally going to, in Matlab, the way you do this is you say at t comma y. This creates a function on the fly that has arguments t and y, and that function is going to be a times y. So that's literally, I have just defined right here a little function that returns a times y. It's not a function of t, but Matlab expects it could be a function of t, so I have to specify that it could be a function of t, even if it's not, and it returns a times y. So this is the ODE fun here. I put in the time span t, and I put in my initial condition y naught. So that's all that this needs. I could have defined a function, in a new file, my right-hand side or my ODE right-hand side, equals a times y. This is just the quick and dirty way to do it in Matlab using function handles. Okay, that's called a function handle. And I'm pretty sure if I run this, it'll be fine. And now I'm going to plot t by y. And y is now this vector, so I only want to plot the first component, the position component. It has a velocity component. I'm only going to plot the position component. And I'll plot it in a different color, also line width 2. Okay, and I'll put in a legend now that the first one is my analytic, and the second one is my ODE45 solution. Okay. And you can see the dashed line and the solid line, they're perfectly on top of each other, meaning that this ODE45 numerical integrator did a really good job of capturing the analytic solution that we derived from scratch with pencil and paper or on this light board. Okay, so really easy to work these things out. In MATLAB or in Python, it's only a few lines. You can do it. If you have the solution by hand, you can just plot it. If not, you can integrate it analytically using this ODE45 function. In Python, it's really almost identical. Okay, so you have to do some more explicit importing. You have to import NumPy and some plotting tools, and you have to integrate this. You have to import SciPy's integrate functionality. This is kind of the ODE45 in Python, is this solve IVP. And then same thing, we're creating a time vector, which is just linear time vector. I guess we're going to divide by delta t at some point, probably. We'll see. There's our same initial condition, our same analytic solution here that you can plot. You can build the same A matrix that we did before and create this little ODE that returns the right-hand side. So this is just like what my function handle in MATLAB was doing. This is returning the right-hand side, kind of what dy dt equals is a times y. That's my linear ODE. And then solve IVP, this is the same as ODE45. It takes in that function handle, that right-hand side vector field that we're integrating, a time span, an initial condition, and which times to evaluate on. And then you can plot everything the same. And the plot's going to look exactly the same. You see here, kind of, again, our analytic and fourth order Runge-Kutta perfectly match each other on this time span. Good. That's what I wanted to show you. So you can solve these by hand by solving this characteristic polynomial by guessing e to the lambda t and solving this characteristic polynomial, or you can write it as a system of first order equations and solve for the eigenvalues of a. That's also going to help you out here. And you can plot these things in, you can solve these and plot these in Python or Matlab. And very importantly, if you confirm that the eigenvalues of this A matrix are in fact the roots of my characteristic polynomial. Okay, I'm going to erase this, I'm going to shut this down, and then I'll just give you two more super quick and dirty examples of these just so you see how it works if I change the coefficients a little bit. So hold tight. Okay, so just a couple more super quick examples. I'm going to fly through these because we know the formula now. What if we have x double dot instead of plus 3x dot, we have minus 3x dot. Plus 2x equals 0. So all we're changing is the sign here. And let's keep our same initial, or some other initial conditions, x0 equals 2, x dot 0 equals 3. Those are our initial conditions. We're going to solve this exactly how we did before. So I'm going to write down my characteristic polynomial. And here's a trick. You can just write down the characteristic polynomial when it's in this form. The characteristic polynomial are literally going to have the same coefficients as the coefficients of these terms. So I'm going to get 1 times lambda squared minus 3 times lambda plus 2, and that equals 0. That's my characteristic polynomial. I'll just show you, if I assumed x equals e to the lambda t, x dot equals lambda e to the lambda t, x double dot equals lambda squared e to the lambda t, and I plug these in. Of course, I'm going to get lambda squared. Everything's going to have an e to the lambda t, so I'm just going to pull that out already. So my x double dot's going to have a lambda squared. My x dot's going to have a minus 3 lambda, and my 2x is going to have a plus 2. All of them times e to the lambda t equals 0. And so, of course, my characteristic polynomial just is has the same coefficients as my ODE. And so we can solve this thing really easily. Let's make sure I don't botch this. So this is lambda now minus 2 times lambda minus 1 equals 0. And so before it was lambda plus 2 and lambda plus 1. And so now my eigenvalues are lambda equals 1 and lambda equals 2. And I should be worried right now because anytime I have a positive lambda, I'm going to get a positive e to the lambda t, and that's going to blow up to positive infinity as time goes on. So this is an unstable system. I can already feel it. And I'm pretty sure that my coefficients are going to be 1 and 1 because I picked it. This is, you can just pause the video and convince yourself, x of t equals e to the lambda 1t plus e to the lambda 2t. You can convince yourself that this satisfies those initial conditions. That's a good exercise for you to do. But this is the solution. And this solution, the other solution, damped out to 0. It decayed to 0 in finite time. We plotted it, we showed it, because these were negative values. So e to the minus t decays to 0. But e to the plus t and e to the plus 2t, these grow without bound. These grow unbounded. There's no bound to how much these grow. These grow unbounded in time, and the word we use for that is, we call this unstable. It's sometimes I feel unstable. These are unstable solutions. These are unstable eigenvalues, okay? And we're going to come back to that later. But so, just changing this sign here and making these eigenvalues positive means that now I have e to the positive lambdas, and these grow without bound. Good. Unstable solutions, literally meaning x goes to infinity as t goes to infinity. Good. Okay, one more example. I'm going to erase, do the same thing. Actually, do I need to erase? I don't. I'm just going to do it right here. Let's do one more example, x double dot plus x dot minus 2x. I'm just checking my notes because I've carefully crafted these coefficients to be really easy for me. X naught is going to equal 3. X dot naught is going to equal 0. Okay, again, we're just going to read off our characteristic polynomial here. Maybe I'll do it in green. Our characteristic polynomial is lambda squared plus lambda minus 2 equals 0. And so I can factor this thing into lambda plus 2 times lambda minus 1. Does that work? Lambda squared plus 2 lambda minus lambda is a positive lambda minus 2. That works. Equals 0. That means lambda equals plus 1 and lambda equals minus 2 are solutions. Again, I can write down x of t equals some constant e to this lambda t plus another constant e to this lambda t. That's a solution. I'm pretty sure based on these initial conditions, we can find that C1 is 2 and C2 is 1. So this equals 2e to the t plus e to the minus 2t. This is a good exercise for you. Just pause and convince yourself that these coefficients satisfy this initial data, these initial conditions. And now what happens here? So this is why I chose this example for the last one. This one has a negative lambda. This is going to decay in time. This one has a positive. This is literally my solution in time. This one has a positive lambda. This one is going to grow unbounded, unstable in time. Now, if I add up something that decays to 0 and something that blows up to infinity, obviously this one wins, and so the system is still unstable. So having even one positive eigenvalue or one positive lambda, even if I add multiple of these, the system is still going to be unstable. Okay, so that's really important also. Okay, good. One last homework I want you to do is for both of these examples, I want you to write down the first order, the coupled system of first order equations, the matrix system version of these. I want you to compute the eigenvalues and convince yourself that those eigenvalues are exactly the same as these lambdas. Okay, that's the last thing I want you to do. All right, next we're going to show what how we get higher order differential equations with like quadruple dots or septuple dots, like more dots, more derivatives, and then how to handle those in exactly the same way. And we're going to build up to general matrix systems and general eigenvalues and eigenvectors. We'll be able to solve every single possible linear system very soon. Stay tuned. Thank you.